Welcome to lecture 11 on electrical machines 1, and we have started discussing about modeling a practical transformer. Earlier we started with ideal transformer, which means that windings has got no resistances, leakage flux is negligibly small, there is no core loss. And then it was so easy, only thing when you connect a load on the secondary side, there will be a reflected current and that will decide the primary current. Similarly, we found out what will be the equivalent circuit referred to the source side, that is primary side, and to the referred to the load side or secondary side. Then we started discussing about practical transformer. I first told that okay, let us first assume that only there exists finite magnetizing current. It is not fully a practical transformer, but only a transformer having a finite magnetizing current. Then that can be taken into account by connecting an external, considering an external resistance to be connected across the primary side of the ideal transformer, XM we called it, magnetizing reactance. Then we considered resistance as well as leakage flux. And finally, last time we obtained the equivalent circuit of a practical transformer as this is suppose the practical transformer, where you apply voltage V 1 and frequency f, then these are the terminal voltages you get at the terminal V 2 and f, same frequency voltage, and these are dots. And so, with respect to these two terminals which are available to me, I can model it as an ideal transformer. Okay. For example, I will model it by an ideal transformer like this. I will assume this is the ideal transformer, and that is this portion is ideal transformer. And then you have connected some resistance and leakage reactance primary, and here is your magnetizing reactance JXM, and then here also the secondary winding resistance R2 and J X2, and this is R1 Jx1. To simplify matter, I am using now, I am replacing XL1, which is leakage reactance standing for, I will simply write it by X1 in order to always writing L. So, X1, X2 small letters I have used because their values are small, leakage flux is small, and this portion is ideal transformer. And this voltage, mind you, these are the two terminals. If you call it A, B, the terminals of the practical transformer C, D, then here is your A, here is your B, here is your C, here is your D, and within the transformer it can be then thought of as if there is an ideal transformer with these external parameters I have connected. And then we have seen how to, this is V 1 F 1 and this is V 2 F 2. What is this voltage? This is your E 1 and this is your E 2. Mind you, there is now distinction between E 2 and V 2, similarly with E 1 and V 1, these two are dots. And if you connect load here, then this current is I 2 phasor current, this is Z 2, and if this ideal transformer we know if it carries current I 2 coming out from the dot, immediately on the primary of the ideal transformer, this is the primary of the ideal, I 2 dash will come, and this is magnetizing current I m. Magnetizing current is produced by E 1, and then to this current is the total current, which will be this current. Because I cannot go inside the practical transformer to see all these things are not there in fact. It is my way of modeling so that everything matches, it predicts correctly. So, this is I 1, this is I 2 dash, this is I m, and this is your I 2. And then we drew the phasor diagram, which I am not once again drawing. Now, only one thing is now left for the which exists in a practical transformer, but we have not taken note of that. That is called the core loss. Core loss. And core loss has two components. One is called eddy current loss, and the other is called hysteresis loss. We will first see why there will be eddy current loss and why there will be hysteresis loss. We try to understand on what factors these losses depend, and then how to take that loss into account by incorporating a resistance in this equivalent circuit. That is the goal, because after all that something becoming the, as I told you, this core of the transformer will become hot whenever there will be a changing magnetic field perpendicular to the area of cross section exists in the core. So, this will be the topic of study today. So, first we take the case of eddy current loss. Okay? That is what we will do. First we will understand eddy current loss, then we will try to impose it on a. Mind you, in a transformer, this was the case. Here is a magnetic material. Okay, and this material has got a a depth in 3 dimension I am trying to draw. This is the core material, okay, and there will be coils here. It goes like this, I am so sorry. Anyway, I will take this one, I will take it out. So, this is the coil, and here we are connecting an AC source, that is the thing. Secondary coil I am not drawing to begin with. Acha, if this is excited from an AC voltage source V 1 with frequency f, then we know there will be current drawn from the supply, which will be flowing like this. Of course, this current will be time varying current, lagging approximately the voltage by 90 degree and so on. But nonetheless, there will be fluxes produced in the core, that is phi t, that too will be time varying. Okay. And the cross sectional area of the core is a rectangle, that is these areas. This is the area, and this area let us assume is constant throughout the core. So, flux will be flowing perpendicular to the area. Any area you consider, that flux is crossing perpendicular to that area. This is called core area, sectional area of the core. This is the thing. Mind you, core is a say ferromagnetic material made of iron, and it is solid like this, and this core material is also conducting. Core material can conduct electricity, because iron, not a good material like your copper, but it also carries current, it can allow current to flow. Core material can conduct current. Okay. Core material means say iron or ferromagnetic material. So, they are good conductor of electricity. Now, if you look at this cross sectional area, the left hand column, I will draw it separately in this way. This is the sectional area, and here is this side I am drawing, understand. This is the thing. What I told, through this these flux lines are coming now, many flux lines. See, these are B or phi. B is also function of time, because phi t is after all B t into the cross sectional area A. This is the cross sectional area. Now, so there is a time varying flux. Sometimes flux will go left hand side. Incidentally, this vertical part of this core material, they are called limb. This is also limb, and these horizontal portions are called yoke. Okay. So, in the limbs, this is the left limb I have drawn, and this winding I am not drawing, it is there. So, I have cut it and trying to figure out what is happening, how flux lines are flowing perpendicular to this cross sectional area. So, this area is here, I have got this sectional area, got the idea. So, this is this. Now, the moment there is a time varying flux, we know that if you have a closed turn, suppose a rectangular turn, you imagine, okay, and there is a perpendicular to this, there is a time varying flux phi t. Suppose a single turn you consider, single turn of conducting material, single turn, and suppose you have a time varying flux perpendicular to its area. Then there will be induced voltage in this turn. What will be the value of this induced voltage? Number of turns, that is 1, suppose single turn, into d phi dt. And what will be the RMS voltage? RMS voltage in this single turn, will be equal to root 2 pi f phi max. Instead of n 1, it is 1. See, this turn is not this turn which makes the coil. What I am telling, I am just considering a separate problem altogether. Suppose there is a single turn like this and you have a induced volt flux which is crossing this coil area in a perpendicular direction, then the induced voltage is n d phi dt and its RMS value will be just like a transformer, and that value will be root 2 pi f phi max into 1. And if this coil is closed, you first imagine as if this coil I have not I have connected a switch, suppose. Then across this coil two terminals, suppose it is opened, that is let me do it like this. Suppose imagine there is a, so there is a flux here. So, between these two terminals then an RMS voltage exists of this magnitude. Therefore, if this turn is closed onto itself, that is this is closed, then I will say there was an induced voltage and now this induced voltage will drive a current in this loop. Why not? Because it has become a seat of EMF, as it happens in any turn in the primary and secondary coil, and it is, if it is closed, then I will say this RMS voltage whatever is induced here, that divided by the resistance of this turn will give me the current, and that current too will be time varying, AC current will be flowing. What will be the direction of the current? If suppose phi t is going up and increasing, then from Lenge's law I know the direction of the induced current in this loop should be such that it will oppose this increase in flux, that is it will be why it went on like this. So, this was my turn. So, the direction of the current has to be like this. Who will drive this current? This induced voltage, and the circuit is already closed if it is a closed loop, and this current has to be like this, so that it can oppose the increase in phi 2 for which the induced voltage is there, that was the cause. So, that will be the direction of the current, it will try to oppose the cause. And if I want to know what will be the, if the current flows here, then there will be power loss in this loop, and that power loss will be I square into resistance of the path if you neglect the inductance of this loop. A single turn inductance is neglected. In fact, to be very correct, I should say induced voltage divided by the impedance of the turn, that decides the current, but I am telling neglect the inductance of this coil. Why? Because single turn inductance is proportional to n square and so on, let us neglect. So, that is this is a information which is true whether you are studying transformer or not. The problem I have stated here, a single rectangular turns, and let us imagine there is a time varying flux going up and down crossing this coil, then there will be RMS voltage induced single turn, that is why n is 1, and this voltage will drive a current, but direction of the current is you have to apply Lenge's law, arguing that let us imagine that flux is suppose increasing in the upward direction, then the current induced in this loop, that is this current must flow in this direction, so that it will try to oppose the very cause for which it is due, that is the Lenge's law. Achha, with this background, let us now come here in the transformer core what is happening. In the transformer core, as I told you, this IT magnetizing current has produced this phi t here, huh? And imagine any section either here or there where not, and every section the same flux is crossing, and it is a solid piece of iron, suppose solid iron. Now, the question is where this fits this thing here. It is like this. If I simply draw this way, try to understand first. This is the, suppose I am looking from the top, this thing I am looking from the top. This is the section, the flux lines are coming out. So, flux lines are, suppose this is the direction of B. I have just shown one line, P is coming out, and if it is coming out and it is time varying, going up and down. Now, what you do? You consider a closed path like this. So, this closed path, I can imagine, oh, there is a single turn here, through which there is a time varying flux like this. Therefore, in this path, in this loop which I have considered, there will be an induced voltage whose value will be root 2 pi f phi max enclosed by this area, not this full phi max. If you consider a single loop like this, then you have to take this area and then calculate what is the phi max there into 1, and this switch is already closed, you have nothing to do. Imagine any closed path through this time varying flux perpendicular to this area, and there will be induced voltage, and there will be, if it is going up, your eddy current loss, direction of eddy current in this single path considered should be like this, because your B is coming out and it will go inside because of this induced current. It will try to oppose that cause. B was increasing upward direction, so it will try to oppose the cause. And this current is called IAD, eddy current. Now, the big question is, this thing, does it happen to this selected so called closed loop? No, it will happen in all the possible. Suppose this is the cross sectional area, you can select a path like this, you can select a path like this. Are you getting? These are paths of eddy current, eddy paths. You can select a path like this. Any closed path you imagine, there will be induced voltage in that loop. You can figure out how much it will be, and that divided by the resistance of this path will give me the current in this loop, next loop, next loop. I mean, therefore, these currents, eddy currents will be, I cannot avoid. If it is a solid piece of iron, and if we are claiming that it is a time varying field exists here perpendicular to this cross sectional area, then eddy currents will be flowing. It is not in the coil, induced voltage in the core, and there will be eddy currents. And because of that, this each of this loop current, I square into R of this path, I square into R of this path. So, if it is a solid piece of iron, you will find it has become hot if you touch this one with your hand. Core material, if you touch, it will become hot. Therefore, there will be power loss. where the power loss takes place in a transformer in the winding resistance, coil resistances R1 R2, whenever they will carry current there will be power loss taking place. That is incidentally called copper loss. That will come discuss in detail, but what I am telling, if you touch the core it will become hot. Why it will become hot? There is no electrical connection between the coil and the core, which is made of say iron, solid iron. The reason, one of the reasons will be because of this, because through the sectional area a time varying flux exists and you choose any conceivable closed path, there will be induced voltage and eddy currents. It may not be rectangular, any arbitrary path loop. Now, after looking at it, if I say okay, the path is like this, will there be some eddy current like this? Yes, it will be. Now, we shall try to understand what should I do to reduce this loss. No mathematics first, physically I mean try to understand why this eddy current loss occurs, because so much sectional area, so many area. It looks like it will be very difficult to calculate the eddy current loss. It is not, in fact, it is not so easy. You have to write field equation, this, that to solve the eddy currents and try to estimate the eddy current power loss. That we have to estimate. But I can understand by applying a common sense that this eddy losses can be reduced if I, instead of using a solid block of iron like this, what I will do, I will use thin plates. Suppose I say there is iron plates, I am drawing it still thicker. This is I will go to next page. What I will do is this core material, this was the solid sectional area of the core, the solid iron. Instead of doing like this, what I can do, I will take plates, thinner plates, and keep them side by side. Thin plates. Are you with me? That is, the plates are like this. You chop this thing with a cutting tools, okay, slices, like your pages of book. Thickness of the book will be achieved. So this is the width of this iron, this was the length, whatever it is, sectional area. The same sectional area can be realized by, instead of using a solid block of iron, thinner plates. That is, you take one plate here, take another plate there, and stack them together, clamp them to get, I think you have got the idea. So, the sectional area from the top, if you look, it will look like this, okay, thin plates. I will show you. Suppose this is a thinner plates like this, magnetic circuit, they are able to see now, thinner plates. You iron plates and you put another like this. I have brought only two, you can put several such plates to have a height here, that is the width of this magnetic circuit, this portion. So, many thinner plates you use of small thicknesses and stack them together instead of using a solid iron. But then Not only that, also what you do, that is very important step. You simply, it is a solid iron, you simply cut it in different pieces, stack them together. No, not like that. Then what you have to do is you have to give a varnish coating to each plate, give a varnish insulation, paint it, varnish insulation, so that each plate is electrically insulated from the next plate. Although they are side by side kept like this, this is one plate, this is another plate. You place it, but between these two plates there will be no current can flow, because this plate is insulated from this plate while you are putting. So, each plate has its own electrical identity, it is not dictated by the others. So, this one, this length, and this is the width. Suppose this is the length, this is the width of this area, this is the width. I can realize that one like this, that area will be realized, and I kept several thin plates together. And then where is your coil? In this previous diagram, if you see, okay, where is the coil? If I draw it like this, the sectional view, where is the coil? Coil must be shown here. This coil, if you look from the top, this is this one. So, coil was here, is not coil. I think you have got the idea. This coil, this primary coil, it should be shown around, it creates flux like that. Anyway, so this will be the RMS induced voltage. Where that fellow has gone? Next page. This was the thing. Therefore, the coil is here, still total flux phi max is primarily decided, as you know, is V 1 by root 2 pi f n 1, is not approximately, at least this is phi max if you give. So, phi max is perpendicular to this sectional area. Coil is here, which has created this phi max sin omega t, and it was doing like this. Here also phi max was in this direction, here also phi max in this direction. Okay. Now, what is the motivation of using this number of plates? Motivation is if it is a solid piece of iron, the area you can have many number of closed path, as I told you, and each one of them is carrying eddy current loss, eddy current loss will be created, losses will be more. So, by common sense, then it looks like instead of using a solid block of iron, I will now do it on this page, so that you appreciate the point. Instead of using a solid piece of iron, if I use thinner plates like this, I am showing the gap larger, so that we understand the point. So, this is a plate and there is phi perpendicular to this, there will be eddy currents now, but if you make thinner plates, the eddy current paths or number of paths available will become less for each of the plates. Getting each plate is electrically insulated from the other. So, if you want to concentrate on a single plate, you will see, oh, in this plate the eddy current loss will be less, because of the thing. Therefore, we will use these plates to make instead of using a solid iron, better use thin plates, thin insulated plates. Instead of solid iron, it will lessen that thing very much, because each plate is electrically insulated from each other, and eddy current will, in fact, if I say this thickness of each plate is so small, you will not find any eddy path existing. Of course, that is not the case. We will discuss it in the next class. This is interesting and try to understand. Our goal will be to find out an approximate expression of this eddy current laws and what factors it depends. Thank you.